Hello everyone, this is Yu. I will present IQ-MPM, interface quadrature maturing point method for non-sticky strongly two-way coupled nonlinear solids and fluid. This paper is co-authorized by Yufang, Liyingqu, Mingcheng Li, Xinxin Zhang, Yixing Zhu, Marie-De Engineer, and Chengfanfu Jiang. As the title suggests, our paper focuses on the coupling between nonlinear elastic solids and fluids. Let's start with watching a few teasers. Top left show a toy bear is flushed by water and the water flows down smoothly without sticking to the bear. Top right is flushing water onto an elastic mat. Bottom left shows a ball floating in a tank of water. Bottom right is squeezing foam into water and produce realistic behaviors. The motivation of this work is to eliminate the limitation of maturing point method and avoid numerical stickiness when simulating solid and fluid coupling. Traditional maturing point method is not trivial to simulate incompressible fluid or free slip interface due to the usage of a shared background grid. Particles that get close will move together and get sticky. Augmented maturing point method solve the incompressibility issue. However, it still suffers from numerical stickiness between different materials. The goal of our paper is to achieving free slip interface between solid and fluid. Simulating solid and fluid has a long history. The first category that was being explored by researchers is the combination of Lagrangian solid and Eulerian fluid. Many of the challenges encountered by Eulerian fluid, such as volume conservation, support for the implicit surface tension, or stable solid-fluid coupling, can be overcome by using a conforming Lagrangian mesh representation. There are some works for Lagrangian solid and Lagrangian fluid scale. Coupling Eulerian solid and Eulerian fluid in another direction, integrating the numerical dissipation becomes essential. Recently, there are also some investigations into hybrid particle grid methods using MPM. MPM naturally supports automatically grid-based collision handling and two-way coupled interactions, while the boundary conditions at the colliding interface is still no slip. Most of these works do not address strong two-way coupling of incompressible fluid with nonlinear elastic solid without requiring multiple monolithic solves. We will start from the governing equations for both fluid and solid phase. Then we derive the weak form of them and think about how could we discretize each of the components. We are inspired by maturing point method, grid-based fluid solver, and traditional finite element method. Eventually, we invent a stable and efficient way to do the discretization and produce nicely behavioral fluid-solid coupling system. Before going into further detail, let's review the background of maturing point method. MPM is a hybrid method which transfers mass, momentum between solids and between particles and grids representations. Traditional maturing point method naturally supports two-way coupling. Due to the interpolation of a single velocity field, maturing point method suffers from numerical stickiness when coupling. If switching to the multiple grids for velocity of different phases, there will be inequality constraints, and existing work has been solving it through velocity projection and post-processing. For more details and explanations on MPM, we have these two course notes for reference on our website. Next, let's talk about how the IQ-MPM works. Let's first talk about splitting strategy. To support arbitrary nonlinear elastic constitutive models, we adopt a different splitting strategy by viewing each solid domain as a combination of hyperelastic component and a meshless ghost matrix material that acts similarly to compressible air. Left image shows that any point from the rest shape of the given object have a point in the current shape and the corresponding differential gradient to measure the change of the shape. We usually define the total energy density on that. However, we can see from the right image that in IQ-MPM, the energy consists of two parts. The first part is F, and is the deformation gradient, and J is the volume change of the ghost material. They evolve independently. Since the meshless ghost matrix material is collocated with the solid, it shares the same velocity field with the solid domain. The meshless and collocated nature of the matrix enforces the equivalence of our solid mass mixture to a traditional solid in terms of mass conservation, momentum conservation, and strength-stress relationship. Let's review all the governing equations first. For both solid and fluid phase, we both have the mass conservation and momentum conservation. We need to deal with different boundary conditions, which includes free surface, sleep boundary, non-sleep boundary, and solid-fluid interface. Some of them has already been handled well in traditional methods like MPM's free surface, where no special treatments are needed. However, others need us to invent new approaches to deal with. Automatically, MPM coupling is inherently restricted to sticky and non-slip interactions. As a result, solid-solid interface experiences infinite friction, while solid-fluid interface experiences numerical stiffness. Without the ability to support free slip boundary conditions, the practical versatility of the MPM is greatly limited, producing animations with visual artificials under certain setups. To remedy this issue, we propose a method to allow for the free slip boundary condition as the interface between solid and fluid domains by only enforcing the normal velocity continuity and the pressure continuity. We are now discussing the governing equations for the solid in details. For the notational simplicity, we are assuming an energy-based solid wall collision treatment and absorb the corresponding stress into this pink term. During discretization, we enforce the ghost matrix continuum to be collocated with the solid continuum. Thus, the solid and ghost matrix share the same velocity throughout the simulation domain. We use the green term to denote the coupled force exerted from the fluid to the solid. The direction of this coupling force is enforced by the normal pressure force. The fully coupled strand nonlinear system is extremely impractical to solve. We draw inspiration from previous work of linear system to cast the fully coupled system into ideal substeps with operator splitting. We first advanced the solid velocity with the fully nonlinear Newton solve, ignoring the matrix and the solid and the fluid. Then we use intermediate velocity in the fully linear coupled equations. This splitting strategy will lead to a simple linear system, further to a reduced pressure-only discretized SPD linear system. We solve for the pressure and substitute back to compute the new velocities. Now let's move to the governing equation for the fluid part. Due to the incompressibility, density does not change over time, so the pink term turns out to be a constant. The momentum conservation equations is now ensuring the divergence-free conditions here. When dealing with the fluid touching slip boundary walls, instead of defining energy in solid phase, we are adding constraint on the velocity and using Lagrangian multiplier in our coupling system. The coupling force is the same as which we apply for the solid and is also along normal direction. Assuming no viscosity, the incompressible fluid domain can be described similarly. While taking the incompressibility assumption that lambda equals to infinity, where lambda is the stiffness of volume change resistance in the constitutive model. For the weak form part, we only take the solid as the example here. With all governing equations that we need, we will multiply test functions onto these equations and integrate them over their corresponding domains to get the following weak form of it. We can see that we need to do integration on the domain of solid and solid fluid interface. There are many possible interpolation kernels for the continuous quantity and test functions in the weak form. We could convert our continuous variables like the velocity v into a discretized variables, which are only valid on grid nodes, not everywhere. You have many choices for the kernel functions to do this kind of discretization. Let's discuss the limitations here. For the NPM solid, the velocity requires at least C1 continuous function to prevent the cell crossing instability caused by discontinuous force. Since mass lumping is typically needed, the particle grid interpolation function in NPM are also needed to be non-negative. We use B-spline function here. With higher order, the sparsity of the constructed matrix will be affected, and the computational cost is usually larger as well. We limited the B-spline degrees to be less or equal to 2, and explore the space of the swable choice. In traditional VP mixed finite elements, it is well known that for incompressible materials, velocity usually should be discretized with higher order polynomials than the pressure to satisfy insubstability and to prevent kinematic locking. With all these limitations, we did a lot of experiments and found the following two choices that are stable and efficient for our algorithm. We represent the orders that we can choose as 5B, which means solid velocity and pressure order, solid fluid coupling pressure order, and solid fluid velocity and pressure order. The first variable choice is B2, B1, B1, B2, B1. Since the solid ghost system and the fluid system are discretized with quadratic B-spline velocity and nodes and linear pressure and cell centers, while the coupling pressure is also linear. Such a node center layout is usually referred to as semi-staggered and proven useful for fluid dynamics. Even though B2, B1, B1, B2, B1 provides a natural discretization, it also leads to a wide gradient operator and a dense pressure stencil for corresponding discretized Laplacian operator. For efficiency and storage considerations, we prefer to discretize with the fluid with a piecewise linear velocity paired with piecewise constant pressure, and coupled with the solid through piecewise constant interface pressure. We label the resulting new scheme as B2, B0, B0, B1, B0. Let's go back to the weak form of our problem. After we discretize all the variables, we need to deal with the integrations now. As commonly done in NPM, we discretize all the integrals that are only associated with solid and matrix using particle quadratures, since particles naturally encode mass, volume, constitutive model parameters, and strength. However, it is still a challenge to discretize the fluid domain. The major challenge lies in the discretization here, which involves integration over solid-fluid interface. A straightforward choice is to construct two level set warping the two domains and reconstruct the sharp interface with averaging. Unfortunately, even though this works fine for two-phase fluids, it's easy to see that the reconstructed level set may only partially overlap one of the two domains in the solid fluid coupling case. If we do fully particle quadrature just like solid particles, we will notice that there are serious instability issues. There are much turbulence in the fluid domain. Another reason we don't apply this approach is that the interface between fluid and solid is still not clear, which will lead to the inconsistency for the degrees of freedom. For the fluid domain, one standard choice is to analytically integrate the interpolation functions. This results in grid-aligned staircase artificials near the boundaries, which has been extensively studied on MAC-grid-based fluid. Expensive cut-cell methods will be needed to deal with this. Instead of the following standard approaches by computing level set-based cut cells, we use particle quadratures for fluid near the free surface and the solid fluid interface to capture subgrid information, just like shown in this image. As we mentioned previously, we emphasize that it is important that the two domains see not only exactly the same interface, but also that each has a complete set of mass massful degrees of freedom on the grid so that the interface is fully coupled by the union of the interpolation kernels of the degrees of freedom. To achieve this goal, we will discretize the boundary integrals through the interface quadrature points, which is IQ points. To ensure the coverage in the solid domain, we sample IQ points directly at the solid particle locations. At the beginning of each time step, we locate solid particles that are within 0.5 dx to fluid particles. For each of such solid particles, we insert an IQ point. To ensure the coverage in the fluid domain, we extend the fluid quadrature points towards these IQ locations continuously. This is equivalent to treating the fluid continuum as closely touching the solid domain when their maturing particles are sufficiently close. Since we already adopt particle quadrature for the fluid volume integrals near the interface, these additional volume quadratures can be easily accounted for by sampling them at IQ locations, and we guarantee that the fluid degrees of freedom on the grid will have kernels brought at IQ points. The interface quadrature method is efficient, easy to implement, and accurate, which makes it our best choice to do discretization for fluid phase. Now we are good to build and solve our coupled linear system. A special treatment I want to mention here is the ghost matrix update. After we solve the system and get the new velocities, the particles can directly interpolate the velocity field and advect using APIC. The solid particles need to additionally update their strength. Since we use a quadratic B-spline kernel for the solid velocity, we can update the solid deformation gradient just like what we do in the traditional MPM, which is green. Here, the ghost matrix particles additionally carry strength J. Natural choices for updating this, including like first setting it to the determinant of the updated solid deformation gradient, or second, involving it using the velocity divergence following MPM treatment of compressible fluid, just like the purple. However, a very simple experiment with dropping a elastic cube easily reveals the instability of these two options. Though through experiments, we also found that we could not observe the instability if we adopt B2-B1 solid discretization. The problem is that with B2-B0, the ghost matrix pressure is required to be discontinuous, and updating it with a higher order velocity field causes inconsistency with discretized choice. Therefore, we instead of interpolating the updated pressure field with a constant kernel to transfer back to the ghost matrix particles and rebuild their strength through red equations. Being consistent with the weak-form discretization successfully removes the instability and results in stable and natural behaviors. Here we show more examples. We can see that the soft creatures with increasing density ratios are dropped and achieve stable floating behavior. A hyperelastic toy armadillo is filled with water. When getting violently stretched, it gets torn apart and water flows out naturally and completely. Our framework supports two-way coupling of incompressed fluid with linear and nonlinear elastic solids. Water fields with different hyperelastic constituent model are dropped on the ground. IQ-MPM can also animate the detailed interaction between the subfluid and granular material. In the end, we raise frogs with water fountains to celebrate the invention of IQ-MPM. This is rendered by particles. This is the realistic version of it. 3 frogs ranging from light to heavy are lifted by fountains while creating beautiful spray patterns during this two-way coupling. Thank you for listening.